Today we're going to be talking about vector resultants. Vector resultants are what we get when we add components of vectors together. The first thing we will need to discuss is a frame of reference. And you may have heard a little bit about frames of reference already. It's a way of communicating a coordinate system to other people, letting them know kind of where we're at, how we're observing. And it can be defined in any way. It most commonly looks just like you would see in math class. So we would have a vertical and a horizontal. Typically we call the horizontal to the right positive x and to the vertical positive y. Now let's take a look at how to add vectors. The direction has to be considered. Remember, vectors have both magnitude and direction. So we can't ignore that direction when we're adding. If both vectors point in the same direction, then we add them just like numbers. We take the magnitudes, add them together, and the direction remains the same. If they point in opposite directions, whichever one we want to call positive, think our frame of reference, we can call whatever direction positive we want. We call one of them positive and subtract the other one, and the direction will match the longer of the vectors, or the one that has the greatest magnitude. And if the directions are in any other orientation, we have to consider components. Let's look at an example of adding vectors. So remember, components are along the axes of your coordinate system. So we're going to look at these two vectors. We have a 25-meter downward vector and a 38-meter leftward vector. The first thing I need to do is define my coordinate system. So in the side, I'm just going to draw a little xy axes. And I'm going to start and say that positive x to the right, positive y up. Again, most of the time we're going to keep it just like you would see in math class. So because these are along an axis, they form a right angle. And we're going to take one vector component and we're going to transcribe it along its axis so that it's still parallel to its axis, but at the end of the other component. That may make a little more sense if I show you. So I'm going to draw out a more formal coordinate system to the right. And I'm going to start with my 25-meter down vector. So I'm going to redraw that. And then on my x-axis, I'm going to draw over 38 meters. So now I'm going to take one of these. It doesn't really matter which one, but I'm going to pick the one on the vertical component. It's easier for me to see. I'm going to transcribe it. I'm going to start it at the end of the other vector and draw it straight down from there. Because, and that may make this a little more obvious now, we now have a right triangle from our origin to the end of our two vectors. So we have our right angle there, and we have our hypotenuse would be our resultant. And because it's a right triangle, we can use the Pythagorean theorem to calculate what our resultant magnitude will be. So remembering that the Pythagorean theorem is a squared plus b squared equals c squared. So a squared plus b squared equals c squared. And we know that our hypotenuse is always c. So I'm going to call this side A, this side B, and our hypotenuse side C. In my calculator, I'm going to type 38, and I'm going to square it. And then I'm going to add 25 squared. So that'll give me 2,069 as c squared. Now to undo the square, again, I take the square root of 2,069, and that gives me roughly 45. So the magnitude of C is 45 meters, but it's not a vector yet. Because it's a vector, I also have to have an angle. And I can use trig functions, sine, cosine, tangent. We typically use the inverse tangent here to calculate the angle. The reason we use the inverse tangent on most cases is because these two numbers here were given. We didn't do any rounding with those numbers. The magnitude of the vector that I found, I had to do a little bit of rounding to get that. So I want to avoid using something that has been rounded. So I'm going to use the tangent, because I remember that the tangent of theta is equal to the opposite over the adjacent. So TOA, tangent, opposite over adjacent. And in this case, I'm actually looking for theta. So I need to get theta by itself. The way I do that is by taking the inverse tangent. So the inverse tangent of the opposite, which based on the angle I'm interested in, is 25 meters. And I divide it by the adjacent, which is 38 meters. And I can type that in. So the inverse tangent of 25 divided by 38. And then I'm going to round it and call it 33 degrees. So the resultant of this vector is 45 meters, 33 degrees below what I've called my positive x-axis. So if I were to report this, I would say my vector is 45 meters, that's the magnitude, at 33 degrees below the positive x-axis. And that reports both magnitude and direction for my resultant vector. Now it's your turn to try. I want you to pause the video once I pull it up. Give this a shot, and then when you come back, I'll walk you through this solution. So we're going to again calculate and express the resultant of the following vector components. We have a 115 Newton vector to the left and a 305 Newton vector upwards. Pause the video here, and when you come back, I'll walk you through the explanation. Okay, hopefully you've given this a good shot. First thing I need to do, define my coordinate system. And again, I'm just going to stick with the one we're used to in math class. I have my x and my y coordinates. Going to redraw them over here a little bit larger. And I have a 115 Newton vector to the left and a 305 Newton vector going upwards. I'm going to transcribe one of them, and I'm just going to take the 115 Newton vector. I'm going to bring it up to the end of the 305, draw it parallel to the axis, and then from here I can draw a resultant from the origin to the end of my new vector. So I have 115 newtons on the top, 305 newtons on the side, and my hypotenuse. Again, I want to use the Pythagorean theorem. We'll call this side B. I'm going to call the right side A, and the hypotenuse I'm going to call C. So again, a squared plus b squared equals c squared. So I'm going to do a squared, which is 305 squared, plus b squared, or 115 squared. And that gives me 13,000. Going to retype this, typed it in wrong. So 305 squared plus 115 squared gives me 106,250. And then to get c, I'm going to take the square root of that, which gives me about 326 newtons. So I have 326 newtons. That is my magnitude, so I can go ahead and bring that down here. So my vector is 326 newtons. And now I need to figure out my direction, so I can add the at. And in this case, the angle I'm looking for, I always want to reference an angle from one of my axes. So I'm going to put my theta there. And again, because I rounded the hypotenuse, I don't want to use it. So I'm going to use the inverse tangent again. So I know theta is equal to the inverse tangent of the opposite, which in this case is B, or 115 newtons, over the adjacent, which is A in this case, is 305 newtons. Again, newtons cancel. I'm left with a unitless value, which is what I want. So I take the inverse tangent of 115 divided by 305, and that gives me about 21 degrees. So theta equals 21 degrees. So my vector, as I express it, is 326 newtons at 21 degrees. And based on my drawing, it is left of the positive y-axis. So when I report this, I would say it's 326 newtons at 21 degrees left of the positive y-axis. Good luck. If you have any questions, feel free to reach out.